Good day and welcome back. This is the first part of our discussion of the derivative as a function, which is really just a continuation of our ongoing discussion of the derivative itself. Let's go ahead and start off with a reminder, which we'll use to set the stage for today's discussion. For a function f of x and a number a, our previous discussion was all about how do we define f prime of a. And we defined f prime of a as a limit of a difference quotient. So we said the limit as h approaches 0 of f of a plus h minus f of a all over h, which is equivalently equal to the limit as x approaches a of f of x minus f of a all divided by x minus a, and implicitly here this is as long as this limit exists. And recall that these above formulas came from motivating examples. The first such gives us the interpretation that a derivative is really an instantaneous rate of change. One of those two key interpretations of the derivative. And then as well, we had the interpretation that the derivative at a point is really nothing more than the slope of a tangent line. So that more geometric interpretation. Now, it turns out that there's really nothing special about finding the derivative at some value a, because of course a could represent any number where these limits make sense. And that indicates to us that we're really talking about something more general. We're talking about a function. So we can maybe, I'll say, just modify our previous definition to think of the derivative as a function. So the derivative of a function f of x is defined to be f prime of x. And note, all I'm going to do is take this previous definition of the derivative at a point, and I'm going to change each of these a's into an x. So this would be the limit as h approaches 0 of the difference quotient f of x plus h minus f of x all divided by h. And note, there are these two limits that can be used to define the derivative, but when we think of it as a function, we are going to stick with just this first derivative. We have the limit of the difference quotient. And furthermore, I'm going to add in there a statement that tells us kind of the domain of the function. So we'll say as long as this limit exists. And note, this final statement is really just being used to indicate that there is some domain. The domain of the derivative would be all values where we can calculate this limit to get the derivative value. Now, we still have the key geometric interpretations that we had previously. A derivative tells us an instantaneous rate of change, and it also tells us the slope of a tangent line. So let me just remind you from our previous discussion, if you wanted to write down the equation of the tangent line to the curve y equals f of x at x equals a. This is a line that goes through the point a comma f of a, and it has slope given by the derivative, so f prime of a. If we write down the equation of that tangent line, it will always fall into the form f prime of a times x minus a plus f of a. And this is most definitely worth knowing because as you proceed through this semester in Calculus 1, Calculus 2, Calculus 3, we will, fortunately or unfortunately, keep asking you to find the equation of a tangent line at a point. So let's go ahead and look at a common example. For this function f of x, which is x plus 1 over x, let's find f prime of x, the derivative, now thinking of it just as a function of x. And then after we've done so, we should be able to, kind of as an afterthought, just state its domain. So using the definition of a derivative, which will always be our starting point, and note it's the only way we know how to calculate the derivative at this point. In our next section, we will introduce some of the so-called shortcut formulas for calculating derivatives. But until we get to that point, we're going to have to go back to this definition, thinking of the derivative as the limit of a difference quotient. If you have had calculus in the past in some context and you've seen these formulas, I know it's going to be difficult, but you're going to have to hold off and wait to use them. So for this example, we are going to use the definition of the derivative. So f prime of x is the limit as h approaches 0 of the difference quotient. F of x plus h minus f of x all divided by h. And I always write this general form as my starting point. For a couple reasons. One, that means I always know what my first step is going to be. And secondly, I always know what my second step is going to be. I need to do this function composition and write out the specific function f of x. And note, to help with that function composition, we just replace x with a blank space. So f of blank is blank plus 1 over blank. And if we're substituting in x plus h, we would have x plus h plus 1 over x plus h. Then we are subtracting away f of x and dividing by h. And we are in this familiar position that we've seen many times now. We have a limit to evaluate, and we need to go back to our previous techniques. So note, as we've typically seen, we cannot simply substitute in h equals 0, but some level of algebraic manipulation is going to be required. Note that the minus needs to be distributed. So we do have a positive x and a minus x. That cancels. And then let's just go ahead and write down those remaining terms. We are dividing by h, and we have in the top an h plus 1 over x plus h minus 1 over x. And what we want to do is get to the point where we can somehow cancel this h off the bottom, which would mean we need to factor an h out of everything in the top, and then we can go ahead and proceed with our limit laws. And the most helpful algebraic manipulation I'm seeing at this point would be to combine into a single fraction. So to get a common denominator, we'll multiply that first fraction by x over x, and the second fraction by x plus h over x plus h. So continuing on, and hopefully using good notation, writing equal signs, aligning in a single vertical column, limits at each step. In the top we have h plus, and now a single fraction whose denominator is x times x plus h. And in the top we have an x from the first fraction and a minus x plus h from the top of that second fraction. And as I've reminded you now a couple times, we have to be careful of distributing. And note, when you distribute that minus through in the numerator of the fraction, you would have this x minus x that cancel off with each other. And continuing on, what we now have is this h in the bottom. In the top we have h plus minus h over the x times x plus h. And notice both of the terms in our numerator involve an h. So let's go ahead and simply pull an h out of both of those. So just algebraic manipulation. So if we pull an h out of the top, we're left with 1 minus 1 over x times x plus h. The h's cancel, and what we have is the limit as h approaches 0 of 1 minus the limit as h approaches 0 of 1 over x times x plus h. We've broken up our limit using the limit laws. The limit of a constant is always at constant. And note, we could continue on applying limit laws, but note that the function that we see here is a rational function in x. So we can simply use the substitution property and go ahead and let h be equal to 0. So that would be minus 1 over x times x plus 0, which leaves us with, finally here, 1 over 1 minus x squared. So what we have is that f prime of x is equal to 1 minus 1 over x squared. And this is a great point to remind you that these problems can involve a bit of work. You should really concentrate on using good mathematical notation, and you might have to have a little bit of perseverance to kind of push through, all of these computations that we see. Now, there was one other question included here: state its domain. And purely by inspection, there's only one value of x that wouldn't make sense, and that would be x not equal to 0. So we have found the derivative, we have stated its domain. And just for fun, we're going to go ahead and take this a bit further, thinking of the interpretation that the derivative at a point gives us the slope of a tangent line. And with this in mind, I would like to ask you, what is the equation of the tangent line when x is equal to 2? So recall from our previous interpretation, with no work whatsoever, we can write down the equation of this tangent line in terms of f and its derivative. We can say y is equal to f prime 2 x minus 2 plus f of 2. So we just have two numbers that we need to determine. What is the derivative at 2? What is the function value at 2? So if f of x is equal to x plus 1 over x, f of 2 is 2 plus 1/2, which we'll just call 5/2. And from our above work, f prime of x is 1 minus 1 over x squared. So f prime of 2 is 1 minus 1 over 2 squared. So 1 minus a quarter would be 3/4. So we now know f of 2 and f prime of 2. The equation of the tangent line at 2 is given by y is equal to 3/4, the slope, x minus 2 plus 5/2. And at this point, we've gone through all of the relevant computations, but just to make sure that we can see this graphically, let's consider a picture. So ahead of time in red, I've sketched the curve f of x equals x plus 1 over x. And the line that we see is the tangent line to the curve at the point 2, 2.5. So remember, 2.5 was f of 2, and the slope of this tangent line is f prime of 2, which we previously computed as 3/4. And we are now at the point where we've spent a significant amount of time discussing the derivative at both a point and as a function, along with the two key interpretations, the slope of a tangent line and as an instantaneous rate of change. And had we been meeting in person, this is where I would have turned the class around to you all. I have a class worksheet for derivatives, which is posted on Canvas. And in class, I would ask you to, turn your desk, work with your neighbors, spend, 20, 25 minutes working on it. So let's see if we can do that here as well. So pause the video, find that class worksheet, spend a good solid 20, 25 minutes, working through the worksheet. And then in our next video, we'll go over several of the examples together. And in addition, you can find full typeset solutions to check your work against posted on Canvas. So stay tuned and take care.